Good day. Welcome to your mathematics live session for today. Looking back at what we did in our previous session for this week, we looked at the concept of two-dimensional shapes. We talked about the fact that two-dimensional shapes are simply shapes in which you can construct on plain paper, or that you can draw in just two axes. So if you have your x and y axis, then every single kind of shape that can be constructed within that x and y axis is simply a two-dimensional shape. We looked at various examples: the rectangle, the triangle, the square, the circle, as well as the basic properties that can exist for all of them. For the rectangle, we denoted the fact that it could have a length and a breadth, or sometimes referred to as the width. And then we could use that to calculate the perimeter, which is simply the sum of all the sides, all the values of the sides. Or it could simply have the area, which is simply the calculation of the product of the two adjacent sides. The same concept works for the square as well. However, for the square, every single side has the same equal value. So when we say we are taking the perimeter of all the sides, we are simply taking the sum of each of those equal sides, which is 4 in number. And then when we take the area, we are taking the product of two adjacent sides which have the same value. So we can just write it as L times L, or as L squared. We then looked at the concept of the triangle and then figured out that for the triangle in itself, we could calculate the area by taking the simple half of the base multiplied by its height. However, we also talked about the different kinds of triangle that could exist, be it the equilateral triangle, be it the scaling triangle, or be it the isosceles triangle. We talked about the fact that the equilateral triangle means that all the three sides are equal, and by extension all the angles being equal. We talked about the isosceles triangle where two sides are equal, and by extension two angles are also equal. And then the scaling triangle where none of the sides are equal. That is if we classify the triangle based on its sides. We then talked about classification of the triangle based on the angles themselves, and then we came up with the acute angle triangle, where all the angles within the triangle are less than 90 degrees. We had the obtuse angle triangle, where one of the angles would be greater than 90 degrees. And then we talked about the right angle triangle, where one of the angles is exactly 90 degrees. We then looked at the concept of circles, and for circles, we had a very in-depth tour as to the characteristics within the circle themselves. We looked at the fact that for the circle, we could generate the chord, which is simply the distance traveled from one point of the circumference to another. And then the longest possible chord within the circle is what we know as the diameter, which takes from the distance from one point of the circumference to another point of the circumference while passing through the center of the circle. Then we talked about the radius being the distance from the center of the circle to any point on the circumference, the straight line distance from the center of the circle to any point of the circumference. And then we looked at concepts like the sector, the segment, the circumference of the circle itself, as well as every single concept that could come in between. Concepts like the arc, as well as the concept of the tangent of the circle. Today, after we have looked at all those shapes, we are now going to go in depth into one of those shapes and then look at various applications that can exist based on those concepts. We are paying much more attention to the triangle in this case. We are now going to use that triangle to extend the concepts into some other very important concepts in mathematics that we have, as well as concepts that could turn up in your exams. One of those important concepts is the concept of elevations and depressions. For this concept of elevations and depressions, the basic property that drives this concept is the property of triangles. So long as your knowledge of triangles is very intact and you have a very good understanding of how triangles work, then studying the concept of elevations and depressions would not be a problem. Now, we have identified that the basic property that fuels elevation and depression is triangles. Now, we have to put in mind or put into cognizance what are the concepts that guide this calculation of elevation and depression, as well as what are the important concepts we have to keep in mind as far as elevation and depression is concerned. That would be where we are going to begin the course today. Now, as a point of important note, the very first concept that we have to keep in mind as far as elevation and depression is concerned is the concept of the Pythagoras theorem. So, we are going to first and foremost, before we delve into elevation and depressions, we are going to pick that basic property that follows it, which is the properties of triangles. And then we are going to pick those properties in detail one by one, and then extend that into the other concepts that come in. Now, the very first property we are going to be picking is the Pythagoras theorem. Now, we already know what the triangle is. We have talked about the triangles and the kinds of triangles we can have based on classifications by sides, based on classifications by angles. We are now picking one of those special classifications, which is the classification based on right-angled triangles. That is where one of the angles is exactly 90 degrees. That is where our focus will be in. Now, consider a right-angled triangle ABC in this form. So, let's consider a right-angled triangle ABC. Let's name this A, B, C. So, in this right-angled triangle, this is obviously the side that is exactly 90 degrees, hence the reason why it's a right-angled triangle. Now, we can classify some sides within this right-angled triangle based on the knowledge of the position of the right angle, which is this. This is 90 degrees. Now, the side directly facing the 90 degree is called the hypotenuse. The side directly facing the 90-degree angle is called the hypotenuse. Ironically, that side that is directly facing the 90-degree angle always turns out to be the longest side out of the three sides within the right angle triangle. Now, in order to identify these other two sides that we have, of course, that means that AB is what we have termed as the hypotenuse. AB is the hypotenuse. We now have side BC and side AC. How do we now know exactly where it falls on? Within this right angle triangle, we have seen that if this is the right angle, then it definitely means that these other two angles left are acute angles. That means they are angles less than 90 degrees. If that's the case, then if I were to pick my angle here, my acute angle here, and call this theta, then the side directly facing this acute angle theta is called the opposite. So, in the choice of the opposite, you need the acute angle theta. In the choice of the hypotenuse, you need the right angle, which is 90 degrees. So, in order to identify where your opposite is, you have to have the acute angle. And then the side that is left, which is usually the side that is beside the acute angle, is called the adjacent. In standard notations, we refer to the points or edges of the triangle in capital letters because those edges translate to the angular values within that triangle. So, we can say that the angle at C is 90 degrees. Sometimes you can have it written as C with a caret on top as 90 degrees. Sometimes you can write it in full form as angle ACB is equal to 90 degrees. So it means that the letter in the middle is signifying that yes, that is the position where the 90-degree angle is. So the angle in the middle, ACB. ACB. So at C, you have that 90 degrees. You can also have it written in this form, or you have it written as ACB. With the caret on top is equal to 90 degrees. So there are different ways you can signify it. Either way you see it within your text is valid and correct, right? And then we can refer to the triangle itself as, we can refer to it as putting a triangle sign and then ABC. So this triangle sign tells us that, okay, we are talking about a triangle, which is ABC. If you want to be specific and know that, yes, it's a right angle triangle you are talking about, you can remove the normal triangle and replace it with something like this. Then they know that you are talking about a right angle triangle. But conventionally, we just use the normal triangle sign. And then in your diagram, with your 90-degree angle, they would know exactly that you are talking about a right angle triangle. So these are notations that can refer to your angles and the triangle itself. One more important notation is the fact that if the capital letter A, B, and C refer to the angular positions, then the sides in front of them can be written as small letters and be denoted as such, which means the opposite which is opposite or which is facing this acute angle can be written as side B. That's a small letter B. This one can be written as a small letter A, and then this one can be written as a small letter C. Right? So you can have those conventions. The sides are written as small letters, the angles are written as capital letters. These are some familiar conventions you can have. Let's now take all of this and go straight into defining the Pythagoras theorem. The Pythagoras theorem is a theorem that relates the three sides of the right angle triangle and brings out a very, very special relationship that exists within the triangles. What is that relationship? The Pythagoras theorem, so I'll just say theorem. So the Pythagoras theorem says that the square of the hypotenuse side is equal to the sum of the square of the other two sides. So the Pythagoras theorem itself is saying the square of the hypotenuse side is equal to the sum of the squares of the other two sides. Now, the hypotenuse side is the side facing the right angle. So you would note that when the Pythagoras theorem is stated, there is no much reference towards the opposite or the adjacent side. We just say the other two sides. Why is that so? It is because the position of the opposite side changes with respect to the position of the acute angle. What does that mean? For instance, if I were to draw a triangle and put my acute angle here, then this one will simply become my new opposite. And then this one will become my new adjacent. However, regardless of what happens to the opposite and the adjacent, I am always sure that because the 90 degree would not change in position, this would always still remain my hypotenuse. So, it is only the hypotenuse within a triangle that exists as a fixed entity. However, what you will term as the opposite or what you will term as the adjacent changes with respect to the position of the acute angle. That is a very, very important factor you must keep in mind. Now, let us now try to write this in mathematics. So, we have said that the square of the hypotenuse side is equal to the sum of the squares of the other two sides. That is the Pythagoras theorem in detail. Now, if we name the hypotenuse side as C and the other two sides as A and B respectively, then mathematically, what we are saying here is that the square of the hypotenuse side, that means C squared, will be equal to the sum of the square of the other two sides, A squared plus B squared. That is all Pythagoras theorem is saying. To find the hypotenuse, take the square of that hypotenuse, and you are sure that that square of the hypotenuse will be equal to the sum of the squares of the other two sides. That is a very, very valid identity that has been proven in every single way as far as mathematics is concerned. This is known as the Pythagoras theorem. Now, we are going to go forward to give examples as to how to use this theorem, and then before we now proceed to the next bit of business we have for today. So, example, we are just going to pick simple examples first. I'm going to draw some set of triangles, and then we are going to go forward to find their sides, as the case might be. So these are some 4 examples. In each case, we have to determine what x would be. I'll go forward to take the first 2 examples, and then you would practice on the 3rd and 4th example to determine the value of x. So what are we saying? Of course, let me note the 90-degree angle. Now, for the first 2, we have to determine x. With the 90-degree angle, you can simply see which of them would be the hypotenuse. You have absolutely no need to even know what the opposite would be or what the adjacent would be in this case. As far as basic Pythagoras theorem is concerned, the most important thing Pythagoras theorem needs to know is what is the hypotenuse. In the first example, we see that the hypotenuse is x. So it means that the hypotenuse is exactly what we are looking for. Now, by Pythagoras theorem, we are simply going to say that x squared will be equal to 3 squared plus 4 squared. So we are meaning that x squared will be equal to 9 plus 16. X squared will be equal to 25. So x will simply be the square root of 25. So x will be equal to 5 units, right? Because we have no other mode of reference. 5 units, right? See and note that even though I picked square root of 25, I'm only picking the positive 5. Of course, you know that square root of 25 should give you plus or minus 5. However, when you are measuring the length of triangles, we measure length in positive values, right? Just as if you take your meter rule, you will find out that every single value of your meter rule is positive. So it means that we are only going to be taking the positive result of square root of 25. Similarly, for the second case, we can see that the hypotenuse, which is the side opposite the right angle, is 13. So we are saying that by Pythagoras theorem, this will simply be 13 squared will be equal to 5 squared plus x squared. That is the sum of the other 2 sides. Now at this point, all we just have to do is make x subject of the formula. We have done subject of the formula before. This will now be 169, which is 13 squared, will be equal to 25 plus x squared. So that x squared will be simply 169 minus 25. X squared will be 144, and then x will be square root of 144, which would give you 12 units. Right? So in the first case, x is the hypotenuse, which is 5 units. In the second case, x is one of the other 2 sides, which is 12 units. Go forward to now find the value of 3 and 4. Attempt it, and if you have an answer gotten, type in your answer in the comment section. Let's have us use some 3 or 4 minutes to attempt these questions. Find the value of x here. Of course, if you look at this carefully, you find out that x is in the hypotenuse position here. However, in this case, x is not in the hypotenuse position. So find out what value of x this is. And then once you do, type in your answer in the comment section. Some of the answers I saw in the comment sections were written in their decimal forms, which is very, very right and very, very correct as well. Getting your answers in decimals are also very, very nice. However, you must also be able to be creative with your answer, especially because of the examinations you have to write. A very good and very, very efficient way of writing it is, even though you are also generating a decimal kind of answer, also try to generate a compact kind of answer as well. And the easiest way to get the compact answer is through your use of short forms. So let's see exactly what I'm talking about. For this number 3, we would have, by Pythagoras theorem, we will have this to be the hypotenuse squared, which is x, will now be equal to 1 squared plus 1 squared. So we are saying that x squared is equal to 1 plus 1. So x will simply be equal to, x squared will be equal to 2. So that x will now be equal to the square root of 2. Now, I can obviously go further and find square root of 2 in its decimal point and get me a value that correlates with that. Your simple calculator can help you do that, so it's very, very fine. However, you can also leave your answer as square root of 2 units, which means that do not be surprised if you write your online exam and then you find out that, for instance, the answer has been left as square root of 2, that is root 2, which is a short form. This is an exact short form. And then you would wonder, what I have is something different. What I have is in decimal forms. Does that mean that I've done the wrong working? No, it just means that they have requested for your answer to be in a compact form. Which means that if you can identify that, yes, this is a short value that is very, very valid, and then yes, you now go further to use your calculator to get in the decimals, then that's fine. In that regard, when you see square root of 2 in your answer, you know that yes, this is a very, very valid result and you can pick it as your answer. So be very, very cautious about how your options in the exam will be. Why? Because the moment you express it in decimal forms, what you will find out is most times the decimal form you would have to approximate. For instance, the decimal form of square root of 2 would give you an approximate value. You would have to approximate to probably 2 decimal places or 3 decimal places, which means that you are still taking off part of the answer because of the fact that you can't write all the decimal places. However, the moment you use it as root 2, the exactness of your answer remains. That is why some examiners would prefer to set questions where the answers would be in this exact form. So always keep that in mind. For the 4th example, we also have this here. In this case, by Pythagoras theorem, we'll have this to be 4 squared will be equal to x squared plus 1 squared. And then this would mean that 16 is equal to x squared plus 1. So let's make x squared so the formula. We'll have this to be x squared is equal to 16 minus 1. X squared will be equal to 15. So x can be equal to 15 units. So I'll just leave them as short forms. I know you can go further and use your calculator to get the exact or to get the decimal result, so that's fine. But short forms which give you an accurate result as well is also fine to get your answer. So I'm sure this has shown you exactly how we can apply the Pythagoras theorem, provided it is a right angle triangle and you can identify the hypotenuse. Now, there is something very, very unique that I want to bring our attention to. If you look at our first 2 examples, you'd find out that the results we got were perfect squares, which means that even when we took their square root, we did not have decimal numbers. We had whole numbers as our results. This means that there are some right angle triangles where the hypotenuse, the opposites, and the adjacents are in a kind of balanced ratio such that all the values are perfect squares. A right angle triangle where all the values of its sides are perfect squares gives those values the name we refer to as the Pythagorean triples. Pythagorean triples are values such that every single member is a perfect square. So, in example 1, the Pythagorean triple is simply 3, 4,